My name is Lily Penn.
And my name is Patel.
And together we're the most world-renowned time-traveling duo. Today we're going to take a look at the packed beds and how they were developed over time.
Packed beds are hollow vessels or pipes that are filled with packing material and are used in processes like separation, purification, or in chemical reactors. Throughout these 5 eras, there have been many different uses and improvements made to these packed beds.
Let's go to the first era.
In the Dark Ages, people used packed beds to filter water using spherical objects like stones and also crushed up pebbles and glass. These were used up until the 19th century until the Raschig ring was introduced in 1914. These usually have equal length and diameters. In the late 1930s, burl saddles were invented. This new shape was much more effective, which can be explained by a concept called porosity. Before we go into that, let's keep going a little farther into our time-traveling journey.
In the late 1950s, a more modern ring called the Paul ring was developed. All rings usually have a high porosity of around 0.6 to 0.9 and a low pressure drop. The Paul rings allowed for more surface contact with the fluid than the original rings while still allowing for high porosity. Finally, the modern saddles were developed. The modern saddles are an improvement to the burl saddle because they have more openings in the saddle in order to increase the porosity while still trying to maintain a high surface area contact. This high surface area contact makes saddles great for interaction between two-phase systems. Packed beds can be used for many different processes, from catalytic reactors, separation processes for one or more phases, and purification. The type of packed beds you choose will depend on what you're trying to accomplish. For example, if you want to have a low pressure drop, then you would want to use a ring with a higher porosity. But if you're more concerned about the surface contact, you may use a saddle even though there's a lower porosity. I feel like we have mentioned porosity a lot, but not even explained what it is. Let's talk about it.
Each of the different particles we've looked at so far have different values of porosity. Porosity represents the space not occupied by the packing material in a bed or column, and it's equal to the ratio of volume of empty space between particles, known as void space, to the total volume of the packed column. Since sphere particles are rarely used anymore, sphericity is also an important factor of packed beds. This corrects for irregularities in shape and cross-section of the particles used. The numerator is the surface volume ratio for a sphere of diameter d, and the denominator is the surface to volume ratio for a differently shaped particle that would normally have a diameter d. Most of the time, though, it's easier to look up these values in a table like the one here instead of calculating this value. The particles are not the only important part of packed beds, but we also have to account for friction in different fluid paths. The Ergun equation describes this flow. It tells us the pressure drop along the length of the packed column and accounts for both laminar and turbulent flow. If the velocity is small, this reduces to only the first term, or the Blake-Cosney equation, and if the velocity is large, it reduces to only the second term, called the Burke-Plummer equation. Ergun's equation is actually the most popular, even though the main thing he did was just combine the two equations that were already derived many years before.
Okay, that was fun exploring how packed beds work. Let's head home. Oh no, it looks like one of our pipes is leaking a toxic gas. If we don't fix this, then we could die and not make it back in order to see our friends and go to our favorite class, transport processes.
Lily explained some of the uses of packed beds earlier, and now we have to use one. The device shown on the right is a fume scrubber, where the toxic fumes flow upward through a packed bed while a scrubbing liquid flows down it. The cleaned air then exits through the top. For the air to be cleaned efficiently, we want the air and scrubbing liquid to have the most contact between them as possible, so the particle shape we're going to choose is a saddle. We also want a low pressure drop, since that will use up less energy, which means we want a lower porosity. In order to decrease the porosity of our saddle, we can choose a modern saddle. We can then use the Ergun equation to do calculations for the system, like finding the pressure drop or velocity of the fluid.
That was a close one. Thank goodness we had our trusty packed beds. Good job today, Maya. Let's head back home.